Hey guys, in this part 3 of Introduction to WebAssembly, we will be discussing about import-export kinds, function, global, table, and memory. Let's start off with function first. We already saw functions in action in our last video. Whenever we export a function from our AS file, the way that we've exported our function here, its exported kind is of type function. If I load this WASM file and see the module, inside exports we can see the kind of function add is of type function. So all in all, whenever you export a function from any assembly script file, its kind would be function. I have added a link to the previous video where I have explained functions which we import and export from assembly script file in detail towards the end of this video. Please do watch it. Let's move on to the global kind now. So global kinds are quite simple. As we can infer from the name itself, global kinds are those kinds or those variables that we declare globally inside our assembly script code. For example, if I declare a simple variable here called const pi and assign it a value 3.14, this variable is globally available to our assembly script file. And if I export it as well, and I'll compile this, and if I load it in our web application, we can see we have pi added here and its kind is global. And if we see the WASM file, we can see we have a global section added. Variable name is pi, its type is float64, and its value is 3.14. So all in all, whatever variable that you declare globally inside assembly script file, its kind would be global, and if it's exported, you can use it as is. So let's start off with tables now. Tables might sound tricky, but they're actually very simple. Tables simply are memory which stores functional references into it. So in JavaScript, we can declare variable like const abc and assign it a value like 12. But instead of raw value, we can also assign reference to it. So now abc is a variable which has a reference to add. In C++, we can assign pointer references as well to a particular variable, which then stores address of that particular function or variable. So all in all, in very simple terms, table is a memory space where whenever we are trying to reference a particular function, that particular reference's address would be stored inside that table or inside that table's memory space. Let's see it in action now. So I have declared this variable here, abc. Let's export it as well. I'll rename it to perform add. And before I compile this, this is our Word file which had add and pi exported. And now I'll just create a new WASM file. So now you might get intimidated by seeing this Word file, but just ignore it. Reason being that whenever we use references in assembly script injects its own code in order to handle errors and exceptions. So let's import it now inside our web application. So when I call load wasm, you can see there is an error here which says that a module environment should be present and it should have an object or a function. So let's see the wasm file and identify what needs to be imported and what we are missing. So it says that environment object should be there, which should have a board, and by seeing the syntax, it's a method that takes in 4 integer arguments. So let's import it inside our instantiation code. So it says env, and a bot function takes in 4 arguments, a2, a3, a4, and I'll just provide empty body for now, and let's load it again. So now this time it loaded perfectly. So let's see what's inside the module. Inside the module, we have 9 things exported. We'll just focus on perform add. Perform add's kind is global here. Why not function? Because we assigned functions reference to it. So Perform adds kind is global, reason being that it's declared as a global variable firstly, and secondly it's not function, it holds the reference to the function. And if we see its value inside the exports object, we see that it holds a value of 1056. We'll see what is 1056 significance, but we can see that there is no table exported here as well. So assembly script provides us export table flag, using which we can export table as well, and it will be present inside the exports object. Let's move to that part now. Let's add that flag, export table. It compiled successfully, and let's load the awesome file again. So inside module, you can see we have 10 things exported now, one of which is table. Let's move on to the export instance itself. Inside exports, we see we have table here. Let's just store it as global variable and see what it contains. So temp1 is of type table. Its length is 2. First one usually is of null reference when we use assembly script, and from second place onwards it holds actual function references which we have referenced inside the assembly script code. But how to fetch that reference? Pretty easy. There is a get function of table using which we can provide the index, and we receive the function's reference. We can see the name $add here, and it points us to this part, this section inside the wasm file. We can invoke it simply by calling it the way that we call function, by passing arguments to it, and it returns us the correct value as well. So use the flag inside assembly script compiler. It returns us table, and table holds references to the functions which we are using inside our code. Let's see what happens now when we have multiple references of the same function assigned to different variables. I'll compile this piece of code and load it again. So as you can see, we have 3 variables that we declared, exported. All their values are 1056, and if I see the table, its length is still 2. You might get the reason why, because all 3 variables point to the same reference, and that same reference is stored here. So no need to create duplicate references. Let's create a new function and see what happens then. I'll create a sub here and perform sub. Load it again. Let's check now. So tables now have 3 values because there are 2 function references now, and if we see perform add 2 and 3 all point to the same address, but sub points to 1088 because it's a different reference. And let's try to fetch this func ref. So let's store this as global variable, and temp1 dot get 2, and I'll just call it passing 5 and 8. So it returned me correct value. 5 minus 8 is minus 3, and this is how table store function references. So there was another thing that I wanted to discuss with you guys. We used export table flag during the compilation. So what that does is it creates the table internally while we're compiling, and then stores the function references there itself and then exports it. But there is another flag called import table. What that means is that assembly script expects the user, or in our case the web application, to provide the table externally so that assembly script can store its references inside that table. See, table is just a memory space, right? So it can be provided externally or it can be created internally as well. So the first flag, export table, creates it internally, and then import table flag expects us to send it as a import object. So let's see that in action now. So I'll pass in the flag import table, and I'll simply just try to load the WASM file now. So as soon as I load the WASM file, it says that there is a module called env which does not have table function as a reference. So the error in itself is quite understandable. Says table import requires a WebAssembly.table. So let's create a WebAssembly.table on our own. So I'll go to main.js and I'll create const table WebAssembly.table. It's a constructor. We'll use new keyword. So now there's a descriptor here. What's a descriptor? Descriptor expects two things. First is initial. Initial is that value that says how many references you actually want to store. Let's just go with 1 now. And next is the element. So element has two values, anyfunc or extern ref. Let's just focus on anyfunc, which means that we want to store functional references here. And we'll pass in as table. Okay, let's load it again. You see, we still got an error, but it's a different error this time. It says that yes, we received the table import, but this time the size is actually quite less. I got one size, but there are 3 functional references that I want to store. First one you remember is empty, and there are 2 other references which are add and sub. So let's increase the value of initial to 3 and see if it works or not. And this time it worked like a charm. And again, you see there is tables here which we provided, but there is no exported table here. Reason being that we already have the reference to the table since it was imported externally. So let's just console log it and see what values do we have once our WebAssembly module is instantiated. So I'll load it again and I'll store as global variable. So temp1 has 3 references, and let's just verify which index points to what reference. So 2,1 gives you 3, and the second reference is subtraction, of course. So this is what import table means. So since it's a memory type of memory, you can either provide it externally or assembly script can create it internally and use it with respect to the size of the program that is. So when we exported 2 functions, 2 functional references, automatically a table was created with size 3. But when we are importing, we have to take care of it, that how much size we actually want to provide to the WASM file. So let's try to understand memory now. So in order to understand memory, let's step back a bit and try to understand how applications work on your machines. So now, whenever you are running a particular executable, that executable is first loaded inside the RAM, which means all your variables, functions, classes, objects that you have declared and used, all those are allocated memory, and then that memory is part of your RAM. Once all those portions are declared, initialized, memory has been provided to them, then your application starts. The same way, WASM file also requires memory to run on your machine or on your web application. That memory is provided by WebAssembly.memory module. WebAssembly.memory module acts as a bridge between a WASM file's code and your machine's RAM. Let's see how it works now. So WebAssembly.memory is nothing but an encapsulation over array buffer, which means it's quite similar to it. In what ways? In simple ways that memory is a linear array where each block represents 1 byte data, similar to array buffer. But there is one difference as well. We can instantiate array buffer providing the number of bytes that it requires. So let's say we created a new array buffer providing 10 bytes. So it will create 10 blocks of data, each block representing 1 byte. But memory doesn't work that way. So the way memory works inside WebAssembly module is that it says, hey, don't give me just a random number the way that you provide array buffer its size. What I need is a page size. So what does page size mean? A page size is equivalent to 64 kilobytes of data. So whenever you are initializing a memory, providing it a page size of 1, it will internally create an array buffer with a size of 65,536 bytes, which means an array buffer with the size of 64 kilobytes. In that sense, WebAssembly.memory and array buffer are different. Now, if you grow your memory twice, what it will do is that it will internally increase the size of array buffer 2 times. Now the size of array buffer would be 128 kilobytes. Let's see it in action now. So let's explore the memory object now. So the memory object has 0 page size, and its array buffer that it encapsulates also has 0 byte length. Let's increase it a bit. So we'll reinitialize memory, and this time I'll provide 1 as the initial value, which means that it has a page size of 64 kilobytes. So if I see memory now, it says, okay, it's of page size 1, but the array buffer has 64 KB length inside it. So 65536, and if we divide it by 1024, will give you 64, which means 64 kilobytes. And if I increase it more, let's say I reinitialized it with 2, this time the memory has page size of 2 and array buffer is actually double now. So if I divide it by 2, the number 65536 or by 1024, 128 kilobytes. So this is how memory increases in batches of 64 kilobytes. And there's another method that we have in memory, which is grow. So we can increase its page size by 1 by passing in the integer 1. And if I press enter, so its size has increased. Now it's triple, like it's 192 kilobytes now. So 199,608, sorry, 6608, single 9, 1024, 192 kilobytes. So this is how memory works, and this is how it encapsulates buffer, array buffer, and this is the root difference between memory and array buffer. Let's move on to the next section now. So let's explore the memory object now. So the memory object has 0 page size, and its array buffer that it encapsulates also has 0 byte length. Let's increase it a bit. So we'll reinitialize memory, and this time I'll provide 1 as the initial value, which means that it has a page size of 64 kilobytes. So if I see memory now, it says, okay, it's of page size 1, but the array buffer has 64 KB length inside it. So 65536, and if we divide it by 1024, will give you 64, which means 64 kilobytes. And if I increase it more, let's say I reinitialized it with 2, this time the memory has page size of 2 and array buffer is actually double now. So if I divide it by 2, the number 65536 or by 1024, 128 kilobytes. So this is how memory increases in batches of 64 kilobytes. And there is another method that we have in memory, which is grow. So we can increase its page size by 1 by passing in the integer 1. and if I press enter, so its size has increased. Now it's triple, like it's 192 kilobytes now. So 199,608, sorry, 6608 single 9 1024 192 kilobytes. So this is how memory works, and this is how it encapsulates buffer, array buffer. So let's also take a look at what is maximum. I'll clear the console and I'll declare a WebAssembly memory again, and this time I'll pass initial as 0 and maximum as 2. So memory is 0. Now if I grow it by 1 page size, its size is 64 KB. Now if I grow it once more, it'll become double now, and now its size would be the double, like 128 KB. But now if I try to increase it by one more time, it'll throw an error. Reason being that we've provided maximum limitation here. So it says maximum memory size exceeded because the maximum size is 128 KB. So this is how you can put the limitation on memory size as well. Now since we have done all that starting stuff, understanding memory and how it encapsulates array buffer, let's just focus on how assembly script manages it internally. So I've created this small snippet where I'm exporting a function called getArray, and I'm also providing a size to it, and it returns me an int8 array. Okay, so I'll generate a WASM file and then I'll try to load it. So you see the exports object provides me two things, getArray and memory, and you see memory is of 1 page size and array buffer has size of 64 kilobytes. Now let's just call this getArray method. So this getArray method would return me an array, and to be precise, it'll return me the index where this array is stored inside the memory. So I created an array of size 10. So the int8 array would be using 80 bytes. Now you can see the array buffer has 64 kilobytes of size. How about we try to overflow that particular memory and see how assembly script's WASM file handles it. So I'll do 1000, and we'll also see what's the status of memory. So it says its page size is still 1, which is fine. So that means that the array that we declared has not overflown the memory yet. So I'll increase it to 10,000, and now again it's 1. Let's increase it a bit more. Let's say 50,000 now, and this time you see the memory increased on its own, because at some point of time during the initialization of the array, the index went out of bounds of the memory, and the memory automatically increased its page size. So this is how if we don't put a lid on the maximum memory that can be used, it just automatically increases its size, which is actually not correct if you see, because there can be memory leakage in our programs. So let's see how we can put a tab on it using assembly script's compiler. So now to put a tab on the maximum memory that can be used by our WASM file, assembly script has provided us a flag called maximum memory. So I'll provide it a value of 1. So whenever we increase the size of the array that we are generating using the getArray method, it'll throw an error if it gets out of bounds of the memory. So I created this WASM file and let's load it. So I got the memory again, and this time I'll just increase it to 50,000 straight away, and we get an error called unreachable. So this unreachable runtime error means that we are trying to increase the memory, but since we've already put a limit on it, which is 64 kilobyte itself, it threw an error called unreachable. We can see here this getArray method is trying to call function 9, and this function 9 actually tries to increase the memory by calling memory.grow, but then since it is not allowed, it throws an unreachable error. And this is how the memory is managed from the assembly script side. So this is how assembly script manages memory internally. If we provide a lid on it, it throws an error called unreachable. If we don't, it just grows dynamically. But assembly script has also given us a provision where the web application in itself can provide the memory so that it can take a hold of how the WASM file works on the web applications. So assembly script compiler has provided us a flag called import memory, which tells the web application that while instantiating the WebAssembly module, you need to provide a memory object as well. So let's try that now. And if I load the WASM file, it throws an error. So it says that the module and env should have a function called memory. I mean, it needs an object called memory, and let's see how to add that. So I'll create a memory the same way that we saw in the previous example, memory, and it needs a descriptor, and I can provide the initial to be 0, and let's just provide it memory, and let's load it now. Now it says the memory import 1 is smaller than the initial. Reason being that if you remember during the compilation of our WASM file, assembly script implicitly gave memory size of 1, which means that while declaring the array and all that stuff, assembly script internally requires at least 64 KB of page size. So we need to provide it so that the WASM file can load and run. So we'll provide 1 here. And let's load it again. Now you see we have received the WASM file and it's got compiled correctly. We can also test out the same thing that we did. We'll just keep a check on memory, and then let's just call getArray 50,000, and this time temp1's memory has increased automatically to 2. So again, we can put a tab on it, and we can simply put a tab on it by providing the maximum as well. So let it be 2, and then load it again, store, and this time I'll call it, and the memory would have been increased. But now if I call it again with an increased number, let's say 80,000 or so, this time it's fine. Let's do 90,000. This time also it's fine. Let's do 1K, but this time it threw an unreachable error. Reason being that it could not grow the memory beyond 2 page sizes, which is 128 kilobytes. And if we see temp1, the memory is still 2. So this is how we can inject memory, and we can put a lid on it, or we can create it dynamically. It's better to put a lid on it, reason being that if there is a memory leakage, we can identify that. Instead, it'll just keep on consuming RAM. So let's move on to the next section now. So while evaluating memory, I found out that assembly script uses around 36 kilobytes of data internally, and the rest of the memory can be used by other initializations. So that is why when we were trying to declare an indent array here inside it, its size can only be increased by 28,652, which is actually in the range of 64 kilobytes. So if the number increases by 1, just 1, so this becomes 68,28652 to 28653, the page size of memory would increase by 1 more dynamically. So it'll turn to 128 kilobytes. So let's see it in action now. I'll load this WASM file, so it has variable, and I'll call getArray, and I'll pass the magic number here, which is 28652. And if we see temp1, the memory still has 64 kilobytes of page size. Now if I just increase this number by 1 more and see the temp1 again, the page size has increased because it overflowed the actual memory that was there. Now, since rest of the page size, the 64 kilobyte that is added is free to us, we can actually create a new array with 64 kilobytes plus the size that is around 28 kilobytes here. So 64 kilobytes turn out to be 65,536, and we can add 28,652 to it. So until this number, our memory will not throw an error because it will be in the range of two page sizes. So it's fine, it didn't throw an error, and memory size is still 2. As soon as I now increase this number by 1, it'll throw the unreachable error, as you can see now. So this is how memory is managed internally. We'll see how array stores its value inside the memory, and then we would be done with this particular video. So just to demonstrate how array works, I'll edit this code a bit, and instead of I32 I'll take in I8 size, and I'll also take a number which would be of I8, and what I'll do is that I'll add the multiplication inside the array itself. So for loop index of I8 type should be less than size, that's it, and the array would have I plus 1 and return I8a. Okay, so what this function does is that it creates a new int array, and then it stores the multiplication of the number that we are passing times the size. So let's output this file and run it. So I'll load the awesome file. I've got the array. I'll store this as global variable and temp1.get array, pass in, let's say 20 and then 3. So I received 36016. So what is this 36016? 36016 is the index of the array buffer present inside the memory from where the initialization of the int array starts. So what happens is that whenever you declare an array, the initial 32 bytes are stored for extra information, and the data starts after those 32 bytes. So the actual data would be found at 36016 plus 32. So at this particular address. So if I store this int array as a global variable, temp2, I'll pass in 36048. So you say it gives us 3, and if I move forward to 9, it gives us 6, 50, it gives us 9, and so on. So let me just open this particular area, 36046, 36048. Okay, so 36048, and here it's the multiplication table of 3. So 3 till 20, and this is how the array buffer or int array, whatever we are declaring inside the assembly script code, is stored inside the memory. Let's see how int32 array behaves and how it uses the memory. What I'll do is that I'll just change this int array to int32 array, and the return type should be 32, and that's it. So let's just build this WASM file and load it in our application, and I'll simply initialize the array data, passing in 20 and 3, and it gave us this address back. So 36016 is the address where our array starts, and initial 32 bytes are being used by the address of the array and its internal handling, and from there onwards we will actually receive the correct data. So if I go to the memory and let me store in data array, and this time temp 2 and plus 32 gives 48, I get 3, which is fine. And if I go to the next address, it's 0. But why? Because in the previous section it was 6, but why is it 0 now? Reason being that in the previous section we declared an int 8 array, which means that a single entry represents 1 byte. But here we have declared int32 array, which means that a single entry inside the int32 array is actually of 4 bytes. So that is why if we are to get the second value, we need to add 4 after 36048. So it would be 52, and then we got 6. And the next entry would be plus 4 again, which is 56, and then we got 9. And you can see it inside this int 8 array. Let's go to this address again, 36048. Okay, so see, 36048 is 3, then we have 6 at 52, 9 at 56, 12 at 60, and so on. And we have to go till 60, and at 1 to 4 we have 60. So this is the difference between int32 array and int 8 array, and how the values are stored inside the memory. If you want the values to be coagulated, you can open the int32 array as well, and inside int32 array I think the address would be 36048. I need to divide it by 4. It's 9012, and if I go to 9012 here, 9012, yep. So we have these values here attached together, because this is a representation of, this representation is of int32 array of the array buffer. So we have these value bunched together. Now if I go to int16, the gap would not be 4, it would be 2. So instead of division by 4, I'll divide it by 2, and 18024 is the address here. So 18024, it's the wrong one. 18024. Okay, so here we have 3, and then at divisions of 2 we have different entries. So this is the representation of array buffer in int32, int16, and int8, and so on. And this is how memory works, and different variables are stored inside the memory.